Hello everybody, I'm Dan. Welcome to my Java and Raspberry Pi programming tutorial series. The order in which my tutorials are organized on both my website at pijava.com and my YouTube playlist is designed to maximize learning by building on concepts from prior tutorials. In this tutorial I'm going to explain the servo control from my previous tutorial. I'm going to open up my web browser to my website, pijava.com, and select Pi Programming. I'll scroll down here to the servo control explained. So this tutorial will pick right up from my Super Easy Servo Control tutorial. Now I'll explain in detail how everything works, including going over some specs on the Raspberry Pi board. Let's go ahead and start back up the Servo Easy program from the previous tutorial. So I'm going to go ahead and minimize that, bring this up, and tell you a few things here. So what I've done is I got my oscilloscope hooked up, the ground wire here to the black, the ground there, and my probe hooked into the white wire, which is our communications wire. And let's go ahead and remote into the Raspberry Pi here. Program is the same as the previous tutorial, Servo Easy, only I changed 152 to 150, and then I recompiled it here. So let's just go ahead and start it up there. Oh, and also in addition to that, I changed some of the delays here too as well. I changed the initial delay to 10 seconds, right? You can see it just moved right there after 10 seconds. And then I changed each one of these first two delays here to 10 seconds so that it'll move here in another few seconds. And then it'll move to another position after that, and then it'll begin doing its loop from one end of the spectrum to the other end of the spectrum after that. So you can see it's just doing its turning from there to there, and so that's basically where we're at on this. And I'm going to show you a whole bunch of cool stuff on the oscilloscope and everything like that. So stick with me. It's not going to necessarily be an easy tutorial here, and there's a lot of concepts I'm going to explain. If you get confused, don't worry about it. Just come in and watch it again, or give it some time and watch it again. Go ahead and you know what? I want to kill that, because otherwise that will be too annoying to try to talk while that thing's going back and forth in front of me here. So Control C, kill that thing. Let's minimize this, minimize that. I'm going to bring back over my website here. Okay, so I'm going to talk a little bit about the servo I've got. And it's just a little generic servo. There's nothing necessarily special about it. But the generic microserver that I'm using has specs that are very similar to over 50+% of the rest of the microservers and standard servos, for that matter, out there. The input voltage for the servo is rated between 4.8 and 6 volts, so the Raspberry Pi's 5-volt output is perfect. There are 3 wires going into the servo: ground, hot, and the communications wire. So let's go ahead and pull that up here, right? Boom. Okay, so in the servo, maybe it's easier to point to these wires as opposed to these, but this purple wire here, this dark wire here, is the ground. The middle wire coming out of here is the hot, and the right wire coming out of here, kind of the light orange one here, is the communications wire. Now out of the Raspberry Pi, this first pin here, comes basically straight through from the power supply for all intents and purposes, and produces 5 volts and about 2 amps approximately. My input on that one is 5 volts 2.2, but my operating system is using like 0.1 or 100 milliamps approximately, or something like that. So the next one over is the ground, which is the black, and the black is hooked in, of course, to this purple wire here, the darkest of all the wires, and this white wire is finally our communications wire coming out of wiring Pi pin 1 or GPIO pin 18, right? And that is going into the orange wire there. Okay. Now the ground and the hot wires actually power the servo's movement, right? While the communications wire merely carries a digital signal. The digital signal controls the position at which the servo will go to and, quote, lock itself in, right? Pulse width modulation, PWM for short, is the fancy term for the digital signal that controls the position of the servo. Okay, so let's talk a little bit about PWM and the servo. Now, if you've been watching all my previous Java Raspberry Pi tutorials, then this paragraph will make perfect sense. If not, then please review them. Now, most generic servos expect the PWM signal on the communications wire to be running at a frequency of approximately 50 hertz. It varies by manufacturer and so forth, but this is kind of I'm getting ahead of myself. So anyway, now some of them can operate between 35 hertz and 333 megahertz, or not megahertz, just hertz, and that should be uppercase there. But 50 hertz is generally the recommended frequency. So let's take a moment to review the math on the hertz calculation. If you remember, 1 hertz is 1 cycle in 1 second. So 1 hertz equals 1 period per 1,000 milliseconds, or 1 second. So if we divide 1,000 milliseconds by 50, we come up with a period of 20 milliseconds. 20 milliseconds is a cycle period of 50 hertz. Excuse me. Let me get some drink. Now, most servos can operate between 15 milliseconds and 25 milliseconds, which means that the hertz calculations can vary from 1,000 divided by 15, right, which equals 66 hertz, to 1,000 divided by 25, which equals 40 hertz, generally speaking. Now, however, for the purposes of this tutorial, we're going to stick with the 50 hertz 20 millisecond period. Trust me, it makes the math much more simple. So the pulse in pulse width modulation refers to the amount of time that the signal is kept high. Most servos go directly to their neutral position, which is about 90 degrees, when the pulse width is at 1.5 milliseconds. So generally speaking, a servo will be at 0 degrees at approximately 1 millisecond and 180 degrees at 2 milliseconds, depending upon the manufacturer. Now, personally, I've seen servos where the spectrum ranges from 0.5 milliseconds to 2.5 milliseconds as well. You really just have to toy around with the actual servo. Now, one more really important thing to note is that the voltage of the communications wire does not need to be the same voltage as the hot wire. Now, the output voltage of 3.3 volts is perfectly fine to generate the signal. So coming back over here to the Raspberry Pi, right? This first pin with the red coming out of it is always 5.5 volts high. You cannot turn that thing on and off, and it just basically passes power through. The white pin here, and most of all the other GPIO pins, I think all of them do really. I haven't tested each one of them for sure, but I'm pretty sure all of them actually only output 3.3 volts. I know this one does. So even if your servo is rated at, for example, 4.8 to 6, or I have another servo I'm going to be demonstrating a future tutorial rated at 7.2 volts, the signal that comes into the servo can be at 3.3. That's just fine. And for example, the amperage flowing out of here, the amount of current flowing out of this red wire here, is about 2 amps, whereas the amount of current flowing out of the communications wire to generate the signal is only about 40 milliamps, right? Which is like really small compared to 2 amps. You know, it's next to nothing. So just so you know that. All right, back to the tutorial there. Okay, so here's kind of a visual representation. We have 50 hertz, a period of 20 milliseconds, and a pulse width of 1.5 milliseconds. This particular illustration will demonstrate a servo going to approximately 90 degrees. Okay, now if we reduce the pulse width to 1 millisecond, keeping our same period and same hertz, right? This will turn the servo to approximately 0 degrees. If we increase the pulse width to 2.0 milliseconds, that will turn the servo to 180 degrees. It's also important to note that don't confuse duty cycle and pulse width here. They're two completely different concepts, right? And if we go over the duty cycle real quick here, 20 milliseconds, 2 milliseconds high, that's a 10% duty cycle, okay? Now, the difference between that and pulse width, for example, on this, is that the period can change, but the pulse width that controls the servo will not change. So, for example, we could have a 25 millisecond period here and a pulse width of 2.0, which would change the duty cycle to something less than 10%, but the servo will still put the its arm position into 180 degrees, right? So the pulse, the length of the period does not necessarily affect much of anything other than, you know, for example, the hertz which it's running at. But it is expecting these pulse widths within each cycle or period to be precisely either, you know, 1.5, you know, or any range from 1 to 2, or from 0.5 to 2.5. But anyway, as you step through those various different values there, it will move it around. Okay, so let's move on here. Let's talk about pin 1 or GPIO pin 18, right? Which is the pin that the white wire is coming out here. Now in my oscilloscope blinking LED tutorial, I demonstrated how difficult it was to generate a reliable signal at 50 Hertz using software. Now that creates quite the issue if we want our servo to hold its position reliably. Now luckily the Raspberry Pi comes with a hardware pulse width modulation built into pin 1 wiring Pi or GPIO pin or GPIO 18 standard. Now, I only wish there was more pins. Using the runtime, the Java runtime class, and invoking the exec method with the string parameter, we can send the setup commands to the wiring Pi GPIO for the hardware pulse width modulation signal, pulse width, period, and hertz. Quite the... I probably could have phrased that a little better. But anyway, so the first command, and let's go back to our program from the previous tutorial here. And so this first command that we're executing here is GPIO mode 1 PWM. Okay, and I'm going to move this off the screen there. So that first command right there instructs the wiring Pi to set pin 1 to pulse width modulation output. Okay, and then the next command, GPIO PWM-MS, right? That one instructs wiring Pi to set PWM, pulse width modulation, to mark space. There's a couple options, mark space or balance, but that's beyond the scope of this tutorial, trust me. Okay, let's talk about the next command here, which is the GPIO PWMC 192. The PWMC is short for pulse width modulation clock, and I'm setting that to 192, and I'll go into the math down here in the rest of this paragraph. The next command of GPIO PMR 2000 instructs the wiring Pi to set the pulse width modulation range to 2000, right? Okay, and then just real quick before I go over why these 192 and this 2000 are here, you can see that the 150 and the 100 and the 200, this is causing it to a pulse width of 1.5 milliseconds, 1 millisecond, and this is 2 milliseconds. All right, now, how did I come up with all these numbers? Now, without going into way too much PWM tech talk, the numbers are derived from the Raspberry Pi pulse width modulation base frequency of 19.2 uppercase M megahertz, and that's 19,200,000 hertz, which basically means you have 19,200,000 periods in 1 second. Okay, and this just reminds me of the old 19,200 baud rate modems, modem days on steroids. You know, blink there if you remember that stuff there. But anyway, we know we need to have a signal, a 50 hertz signal with a period of 20 milliseconds. So that's easy math. 50 times 200 equals 1,000 milliseconds. Now I'm probably going to lose you on the math logic here, but don't worry if you do, it won't really matter. Ultimately, I want a ratio of 1 millisecond to 100 thingamajigs. Okay, and this kind of goes back to this, specifically this one right here, right? This parameter right here is going to equal 1 millisecond. Okay, I'm calling that a thingamajig for now. So when I pass the argument of 150 thingamajigs to the command GPIO PWM150, it will create an exact pulse width of 1.5 milliseconds, right? And that is this one right here, right? Which is going to make it go to like its center 90-degree position. So I take my 50 hertz times 20 millisecond period times 100 thingamajigs ratio equals 100,000. 100,000 is my magic number. Now, to get the pulse width modulation clock, I divide 19,200,000 divided by my magic number of 100,000 to get 192. And that explains the GPIO PWMC 192. To get my pulse width modulation range, I need to divide 100,000, my magic number, divided by 50 hertz equals 2,000. And that explains the GPIO PWMR, the range, 2,000. Now, I want to emphasize, don't even worry if everything above makes absolutely no sense. I just decided to go into detail for those of you that are curious about how I came to the numbers and the math. Okay? Now we simply change the last argument for the GPIO pulse width modulation 150 to get a pulse width of 1.5 milliseconds, or 100 to get a pulse width of 1 millisecond, or 200 to get a pulse width of 2 milliseconds. By setting the ratio of 1 millisecond to 100 thingamajigs, I can have precise control over the angle of the servo. Now ultimately, when a servo is hooked up to the steering column of the Toyota Land Cruiser, I will have a nice, smooth, precise steering motion instead of a jerky, spazzy motion, which would result from a less precise ratio. Okay, so let's go ahead and see some stuff in action. Let's pull this back over here. Let's pull up that there, and let's start back up our program again here. All right, so there is our, that is basically 1.5 millisecond pulse width. There is what you're looking at here. And after 10 seconds, it moves it to just a little bit over there. And then after 10 seconds, it'll move it back to the other one there, okay? All right, so now what I'm going to do is adjust my, and then it'll start going back and forth. But I'm going to adjust my camera here so we can actually see the screen of the take a moment to just get this kind of precisely there. So maybe I'll scoot my servo back just a hair to get that in there. And then let's refocus the whole thing. Okay, so I am going to come over here and Control C on that to stop that thing. And then I'm going to start her back up, okay? So right here I've got you can see here's period, right? And it's currently 20 milliseconds. Frequency is 50 hertz. My pulse width just went down to 1 millisecond, right? And now it's going to jump up to 2 milliseconds and about the other thing. Ignore duty cycle over here. Okay, it just jumped up to 2 milliseconds there. Okay, and as this starts going here, this width, which is our pulse width, is going to be changing, as you can see, anywhere from, well, I set it actually, you know what I'm going to do? I'm going to come over here and I'm going to do Control C. In the last part of my tutorial, I changed these values to 242 and all the way down to 53, which happens to be the max values on this one, which would range from about 0.5 milliseconds to 2.4 approximately. So, but we want to change this to, this is a 100-to-1 ratio, so we're going to make it go between like normal servo values, even though this one that I've got can go a little bit outside of that range there. Okay, so we'll come back up here and compile this and run it, and so you can see right away our pulse width is at 1.5 milliseconds, and what you'll see up here is this is actually representing the oscilloscope is actually catching that up there. So we're currently at 1 milliseconds. This little width up here, which is our pulse width, it just doubled itself, and as you can see, the servo just spun right down there. Okay, so now when it starts going from end to end, we're going to go with a pulse width basically of 1 millisecond all the way up to the, you know, I need to slow that down so we can actually see those numbers jumping around, right? Because I've only got a 10 millisecond delay in between there. I'm going to change it to, oh, let's go with like a 50 millisecond. Let's see if that's good enough there. All right. And start running it again. Yeah, this is gonna just, I'm gonna save a few seconds if we run this multiple times. I'll have it hold in the center and then the min and max for only 5 seconds. Okay, so 1.5 milliseconds, you can see the width of the pulse up there. 1 millisecond, it got shorter. And now our max range, 2 milliseconds up there. And now we'll start cycling in between there, and you'll see this gets shorter. And then it'll get, you know, all the way over to the end here, and then all the way back. And you'll see some, like, down here on the low side, it goes a little bit below. You don't even worry about that doing that. We're just primarily concerned with this nice clean signal right up here. Okay, and so you can see the pulse width servo turning, so we get all the way up to the max there and then all the way back down and so on and so forth there. So anyway, so that's kind of what I wanted to show you guys there. Just leave you with a quick final thought there, and that'll pretty much do it. So anyway, stay tuned for my next tutorial where I will show you the remote controlled Toyota Land Cruiser and discuss the reasons why I chose the vehicle for the project. Thanks for watching.